Alright, hi everyone. Going to continue on with the videos and make a video for section 3.4. I apologize to everybody for not making it to class on Tuesday. I was just feeling absolutely awful. I was feeling terrible. So I stayed home, got some rest. And remember, for the last two sections, there's only two more sections to go through this quarter, 3.4 and 3.5. I will be making videos and then helping people do homework in class during class time. So make sure if you have a laptop, you're bringing your laptop. If you don't have one, you can always use mine, or you can use the computer in the classroom to do your online homework. Or look at the textbook to do some written homework problems. And what we're going to do is, so in this section, or in this chapter so far, 3.1, we discussed exponential functions, a little bit about transformations, what the graphs look like. In section, also in 3.1, we did a little bit talking about how to find functions that model percent growth or decay. I made a video talking about compound interest. Section 3.2 was talking about inverse functions. Again, made a video, helped people go through problems in class. I just recently posted a video for section 3.3 covering logarithmic functions. And we're going to spend a section talking about logarithmic identities. Section 3.5 is going to be exclusively about solving logarithmic and exponential equations, and to do that we need some logarithmic identities. So, theorem 3.3, this is what's called the product sum identity for logarithms. Now, the logarithm of a product of two positive numbers, m and n, is equal to the sum of the logarithm of m and the logarithm of n. So what this is saying is log base b of m times n is equal to the sum of log base b of m and log base b of n. Okay, now I will show you where this comes from. So if what you do is, I'll show you why this property is true. If you let m be log base b of capital M and let lowercase n be log base b of capital N, there's a conversion formula that I believe I showed you in the last section. The first, lowercase m being log base b of capital M, means that b to the lowercase m equals capital M, and lowercase n being log base b of capital N means that b to the lowercase n equals capital N. Okay, so now when I start working with the left-hand side, if I look at log base b of capital M times n, I can rewrite this as log base b of, now capital M is now b to the m times n, which is now b to the lowercase n. You can use properties of exponents. Okay, whenever you multiply things with the same base, I'm going to add these two exponents, which gives me log base b of b to the m plus n. And the way you can think of this is if I do log base b followed by exponential base b, those kind of undo each other because they're inverse functions, and I would just get the power m plus n back. So this equals m plus n, which if you go back to the beginning, I let lowercase m be log base b of capital M, and then lowercase n was log base b of capital N. So that verifies that property. So it does come down to using your conversion between exponential and logarithmic form, and then using a property of exponents. When you multiply things of the same base, you add the exponents. And then I used an inverse property. If I do the log base b function followed by, well actually if I do the exponential base b function followed by the log base b function, those are inverse operations and they undo each other, and I just got the exponent back. Okay, so let's do some examples seeing how to use this property. Okay, so example 1, I'm supposed to simplify log of 25 plus log of 40, and I'm going to do that using the property mentioned above. Now, this property goes both ways. So here's the property itself. Log base b of capital M plus log base b of capital N is log base b of the product m times n. Okay, so if I'm doing log of 25 plus log of 40, I can combine those two to a single logarithm if I multiply 25 times 40. This would be log of, now 25 times 4 is 100, and then 25 times 10 is 250, and 100 times 250, I believe 25 times 40 would be 1,000. And now, when you have a logarithm and there's not a base written there, the base is assumed to be 10. So remember from the previous section, if I want log base 10 of 1,000, I need to know what power of 10 is 1,000. So what would I have to raise 10 to get 1,000? And the answer is 3. So that's the answer. And that's because 10 cubed equals 1,000. Okay. So log of 25 plus log of 40 using a logarithmic identity, the sum to product formula, or the product to sum identity, that just equals positive 3. Okay, example 1, part B. It says write log base 4 of 4x minus 12 is a sum of logarithms and simplify. Okay. So again, using the sum to product identity. Now, before you can use the identity, you have to write the argument or the input of the log as a product, which would require you to factor out the 4 first. Okay, so if I pull out the 4, I'd be left with x minus 3. Now I have a product. Okay, the 4, I'm thinking of that as the capital M, and the x minus 3 I'm thinking of as the capital N. So this would equal, if I use the product to sum identity, this would be log base 4 of 4 plus log base 4 of x minus 3. Okay, and of course, the first one, the log base 4 of 4 part, to compute this, you're asking yourself, okay, so the base is 4. What power do I need to raise the base to get the input of 4 back, which would be positive 1? And there's not much you can do with the second term. That would just be log base 4 of x minus 3. Okay, so that is part B. Now we'll take a look at part C. Okay, so I'm supposed to write, this time taking the expression 2 plus log base 4 of x minus 3 plus log base 4 of x plus 4. I'm supposed to write that as a single logarithm of a second degree polynomial, in other words, a quadratic, right? A second degree polynomial is just another way to say a quadratic function. Okay, so I'll start with my expression 2 plus log base 4 of x minus 3 plus log base 4 of x plus 4. Now, what I'm going to start doing is, ultimately I want to write this as a single logarithm, and I'll start by combining the second two terms first. So this would be 2 plus, okay, the sum of the second two terms, since I'm adding two logarithms base 4, what I can do there is I can multiply x minus 3 and x plus 4 together. Those are being thought of as my m and my n. And I'll do one more step. This would be 2 plus log base 4, and I would just FOIL or multiply that out. x minus 3 times x minus 4 would be x squared, a minus 3x, so the minus 3x plus the 4x would be a plus x, and then of course the last term would be negative 3 times 4, which would be a minus 12. Okay, so now I have reduced it to two terms, and how am I going to write this as a single logarithm? Well, this is going to come down to rewriting 2 in terms of log base 4. Okay, so 2, if I want to get that as a log base 4, okay, so I have to think of what would I take log base 4 of to get back a 2? Okay, well, I would take log base 4 of 4 squared, which is 16, because 4 squared is 16. And I have plus log base 4 of x squared plus x minus 12. And finally, the last step, I can combine this to a single logarithm, thinking of 16 as m and that quadratic as n. So I can do a single logarithm and I can multiply together, and I'm going to distribute at the same time 16 times x squared plus 16 times x minus 16 times 12, which is 160 and 32. I believe you'll get a minus 192. I have now used the sum to product property and combined the original expression to a single logarithm. Okay, next is the quotient difference identity for logarithms. So this time if you have a single logarithm, log base b, again m and n have to be positive. So if I take log base b of the quotient, okay, the way this works is you would take log base b of the numerator, and this is a little bit different. The product log of a product becomes a sum. The log of a quotient becomes a difference, and I would subtract log base b of the numerator or denominator n. Okay, so now part A. Say I want to simplify log of 20,000 minus log of 20. So I can go the other way. I can combine those to a single log, and since it's a difference, I will take the input on the first log, 20,000, and divide by the input on the second log. So I get log of 20,000 divided by 20. This becomes log of, and 20,000 divided by 20, I believe, becomes 1,000. And remember this, if a logarithm does not have a specified base, it is assumed to be 10. And log base 10 of 1,000 is the power you raise 10 to get 1,000, which would again be positive 3. So that's the answer, and it's because 10 cubed equals 1,000. Okay, so there's part A. Log of 20,000 minus log of 20 simplifies to positive 3. Okay, so next example. So I'm going to write log base 4 of 1 over x minus 2 as a difference of logarithms and simplify. So I will start, take my log base 4 of 1 over x minus 2, and my numerator is going to be my m, the denominator x minus 2 is going to be my capital N, so I can do log base 4 of the numerator, positive 1, minus log base 4 of the denominator, x minus 2, and this will now equal, so I can compute the first one. Log base 4 of 1 is what power do I need to raise the base 4 to get 1? Well, the only thing I can raise 4 to get back 1, the only power I could use would be 0. So I'd get 0 minus log base 4 of x minus 2, which would just be minus log base 4 of x minus 2. Final answer. Okay. It's a pretty atrocious 4 base that I have down there. There we go, that looks better. Okay, next example. Okay, so I have a difference of 2 logarithms. I'm supposed to write it as the sum of 2 in a logarithm of a first degree polynomial. Remember, a first degree polynomial, that's just another way to say a linear function. Okay. Okay. So, start with my log base 3, 9x squared minus 9, minus log base 3 of x minus 1. And let's deal with the first logarithm first. So what I'm going to do is, notice 9x squared minus 9, you can factor out the 9 and be left with x squared minus 1, and then I still have the minus log base 3 of x minus 1. Okay. And then in the next step, the first logarithm, there is a product. You can think of 9 as the m, and you can think of x minus 1 as the capital N. This will now equal log base 3 of the first value 9. Since it's a product, you will do plus log base 3 of x squared minus 1. And I still have the minus log base 3 of x minus 1 on the back. So here's where the 2 is going to show up. This is supposed to end up being 2 plus a logarithm of a first degree polynomial. Now log base 3 of 9, okay, when you compute a logarithm, you say, what power do I have to raise the base of 3 to get 9? Well, that would be the power 2 plus. And then what I'm going to do with my second pair of logarithms, okay, so I'm supposed to do 2 plus a single log of a first degree polynomial. Now I can use the quotient difference identity to write that as a single logarithm. The first input is x squared minus 1, that goes in the numerator. And then, so remember that's my m, that's my n, and I can divide by the x minus 1. This will now equal 2 plus log base 3. Now the only way that this is going to become a logarithm of a first degree polynomial, you have to factor the numerator. X squared minus 1 is x plus 1, x minus 1. The x minus 1s will cancel, and sorry I have to write this up here. The final answer would be 2 plus log base 3 of the first degree polynomial x plus 1. Excuse me. So there is my final answer. I wrote it as the sum of positive 2 and the logarithm of a first degree polynomial. Okay, and the last and third property of logarithms is called the power product identity. And it says the logarithm of a positive real number m raised to a real power p is the product of p and the logarithm of m. So what this means, essentially, if I zoom in, this means this power p, so if I take log base b of an exponential expression, basically, the power p can come out front, and this then becomes p times log base b of capital M. Okay, and again, I showed you, or I proved or verified the first identity. In the quotient difference in the Power product identities can be shown in a similar way, but I will not make you responsible for that. Okay, so example 3, it says, use the product sum and power product identities to write log base 5 of 25x to the fourth strictly in terms of log base 5 of x. So that kind of means that essentially what this means is that the expression should have log base 5 of x appearing in it. So that you can kind of think of that as like a variable in itself. Okay, so now log base 5 of 25 x to the fourth. It says to first use the product sum identity. So 25 is going to be the m, x to the fourth is going to be thought of as capital N. And you can first break this up into a sum of logarithms, log base 5 of 25, plus log base 5 of x to the fourth. Okay, next, we're going to do a couple things. First, if I look at the second term, I can now use the power product identity to bring 4 in front of the log. And then log base 5 of 25, we should be able to figure out what that is. Okay, log base 5 of 25, so if I look at the first term, again, what this will equal is the power I need to raise 5 to get 25, so that'll be positive 2, plus, and then on the second term I will bring the 4 in front of the logarithm, get log base 5 of x, and then I would be done. So I've used the identities and written the original expression in terms of just log base 5 of x. Okay, next I'm going to use the product to sum and power product identities to write ln 3 plus 2 ln x plus 10 ln z as a single logarithm. Now remember, natural log of x is just a special notation for log base e of x. So if I want to write this as a single logarithm, the first thing I'm going to want to do, let me switch colors, is notice the second term and the third term both have a constant in front of the logarithm. So what we're going to do is we're going to bring those up and use the power product identity to make those powers on x and z respectively. So I will leave the first logarithm alone, and the second term, 2 ln x, becomes ln of x squared, and the third term becomes ln of z to the 10th. Okay? And the next step is I can probably look at the first two terms and combine those to a single logarithm first. That would give me natural log of 3x squared plus natural log of z to the 10th. And now again, thinking of 3x squared as m, thinking of z to the 10th as n, this is going to equal natural log of the product of m and n, 3x squared z to the 10th. And there's your final answer. The original expression is written as a single logarithm. We're going to see that this is going to be really important to be able to do this later when we're solving logarithmic equations. And finally, last part in example 3, we're going to use all three identities, the power product, the quotient difference, and the product sum identity, to basically decompose this logarithm. So notice in the previous problem we took a sum of 3 logarithms and combined it to a single log. This time we're going to break apart log of the radical or square root of x to the 5th over 3y squared, and we're going to fully decompose this and write it in terms of log x, log 3, and log y. Okay. So if I do logarithm of the square root of x to the 5th over 3y squared, the first step is going to be to recognize that a square root is really just the same as taking the 1/2 power. Okay. Then what I would do from here is probably use the power product identity to pull the 1/2 out front. So this would equal 1/2 times log of x to the 5th over 3y squared. Now I'm going to introduce some brackets, because if you look, the log of this quotient, you can think of x to the 5th as m, and you can think of 3y squared as capital N, and you can break this up into a difference of logs, so I can take log of 1/2, and so the 1/2 stays out front. I introduce brackets, because the log of the quotient becomes a difference of the logarithm of the numerator and the logarithm of the denominator. Okay, this will now equal 1/2. Now, a couple things I'm going to do. The 5 is going to come in front of this first log, so I get 5 times log of x minus, I need to introduce parentheses because now I'm going to use the product sum identity. The second term, log of 3y squared, would become log of 3 plus log of y squared. Okay. And I can see that I'm already going to be running out of room. Let me erase my first step here. Okay, so if I come back to my original equality, this is going to be 1/2 times 5 log x. Now I will distribute the 3 through both of these, or the negative, sorry, so I get minus log of 3. And then another thing I'm going to do is I'm going to also bring this 2 out front while distributing the negative, so I'll get a minus 2 log y. And then finally the last thing would just be to distribute the 1/2 through. So I get 5/2 log x, so there's my term with log x, minus 1/2 log 3, there's my term with log base 3, and then 1/2 times negative 2, my last term would just be minus log of y. So there's the expression decomposed and written in terms of log x, log 3, and log y. Okay, now lastly is to cover what are called base conversions, and what these are really saying is that any exponential function or logarithmic function can be rewritten either in terms of base e or base 10. Now I'll show you the first one here. These are coming from inverse properties. So b to the x can really be written as e to the natural log of b to the x, because if you think about it, the e and the ln are inverses and they undo each other. And then you can just bring the x out front, which is how you're getting e to the x natural log of the base, and you could do the same thing with the power of 10. The next one is not as easy to show. I could show you if you like, but I don't think I'm necessarily going to do it. But basically these are the conversion formulas. The benefit of this formula right here is if I wanted to do, say, log base 4 on my calculator, your calculator only has a natural log and a log base 10 button. So that's one reason these are really useful. Another useful, I guess, reason to write this is it shows you that log base b of x is a transformation of natural log of x by the vertical scaling factor 1 over natural log of b. Or it's a transformation of log base 10 by a vertical scaling factor of 1 over log base 10 of b. Okay. So every exponential can be converted to a horizontally scaled exponential, a horizontal scaling of the exponential function e to the x or 10 to the x, and every logarithmic function can be converted to a vertically scaled logarithmic function base e or base 10. Okay. So converting bases. So part A, it says write log base 3 of 14 in terms of the natural logarithm. This would be natural log of the input over natural log of the base. And it says use your calculator and find the value of the logarithm and round to 3 decimal places. And I get 2.402 when I use the second, like if you hit the green second button and then hit the LN, sorry, you just have to hit the LN button on the calculator. You get 2.402. Now you can do the same thing in part B, log base 3 of 14. I can write this in terms of the common logarithm as log of 14 over log of the base 3. And there's a log button on your calculator. If you do log of 14 over log of 3, you will also get 2.402. Okay, now the next problem says convert f of x equals 1.052 to the x into an exponential function base e. So you can write this with base e. So it's always going to be e to the natural log of x times, sorry, e to the x times natural log of the base 1.052. So I've now converted it to an exponential function base e. In part D, it says convert log of x to a vertically scaled natural logarithmic function and describe the vertical scaling. So g of x is log of x, and there's secretly a base 10 down here. This can be rewritten as the natural log, so ln of the input x over natural log of the base, and I can write this as 1 over ln of 10 times natural log of x. Now this 1 over ln 10 out front is your vertical scaling factor, so I can say g is a now 1 over natural log of 10 is bigger than 1, so c is less than 1. Okay, or this 1 over ln of 10 is less than 1. So g is a vertical compression of ln of x by a factor of 1 over natural log of 10. Okay, that's it. Make sure to take a look at the homework. The online homework will certainly be open by the time you have access to this video, and I will post written homework problems shortly. Thank you for watching. If you have questions, let me know. Make sure to watch the video, look through the homework, come to class, and get as much of the homework as you can done in class. Thank you. Have a good rest of your day.